All right. Welcome everyone to the Northwest Quantum Nexus seminar series. Thank you so much for your flexibility in clicking a second link potentially and joining via Zoom today. We are recording the meeting and the seminar. This will include your questions, your comments during question and answer sessions that can occur throughout the talk. So please be aware of that. You should have also accepted that when you joined our Zoom call. Also, please recognize we do have a code of conduct. We are dedicated to providing a respectful, a professional, a friendly, inclusive environment for everyone. So please do, bring that culture and behavior forward today in terms of being inclusive and respectful and professional. And we don't tolerate any behavior that is outside of that. So thank you very much for adhering to our code of conduct, and you can read it on the slide that's up right now. I'm very honored and excited to present Dr. Tahan today. Charlie Tahan is the Assistant Director for Quantum Information Science and the Director of the National Quantum Coordination Office within the White House Office of Science and Technology Policy. And his office ensures the coordination of the National Quantum Initiative, for example, and various quantum information science activities across our federal government in the US, industry, and academia. Charlie also continues to serve as the chief scientist and the director of the LPS Qubit Collaboratory, Laboratory for Physical Sciences. He's a practicing physicist, also helps mentor, guide, and work with many students in the field. And he's been recognized as Researcher of the Year, received the Presidential Early Career Award for Scientists and Engineers. He's a fellow of the American Physical Society, and also a fellow of ODNI Science and Technology. It's wonderful to have Charlie here today presenting and speaking about just qubit. So we're going to learn from Charlie on how to just qubit. Great to hear about the latest research and your unique perspective in these positions that you have led on behalf of our country. So thank you, Charlie, for taking us on this tour today. And we will have time for questions. Feel free to post questions in the chat or raise your hand as well. Thanks, everyone. Turning it over to you, Charlie.
All right. Well, thanks, Krista and Nathan and all for inviting me and saying such nice things. It's always surprising. Nathan asked me to give a technical talk today, so I'm going to talk about qubits. What I spend most of my scientific life talking about. So I'm going to share my screen now. And this is going to be a lighthearted talk. I'm going to highlight a lot of the stuff we've been working on or thinking about over the last year or two. And please, ask questions. I'll have some breaks to look at the chat or answer verbal questions. Okay, so just qubit. It's a joke, like just do it from Nike, right? You guys are in the Pacific Northwest, so I thought it would be apt. I like to start off all my talks these days with the slide on careers. Every talk should be a career talk. And the point I like to make is that there are a lot of different ways to contribute to moving quantum forward to science. A lot of different ways to have impact. Obviously, as a research scientist, coming up with great ideas that other people adopt. But also, there are many other ways. And I've been fortunate to take a somewhat circuitous route, in my career. I was a CETA or a technical consultant to DARPA and helped them launch some of their big quantum computing programs. That's one way to have a lot of impact on something field you care about. I've led organizations at LPS, which is the physics research arm of the NSA at the University of Maryland. Also been a technical lead there. And then now I'm on detail to the White House, trying to make policy for the National Quantum Initiative. So many different ways. I'm going to give you a few examples throughout my talk, but I'm going to mostly stick to physics stuff. Okay, so there are a lot of different qubits. We're all, and this talk is really from the perspective of quantum computing. I tend to care about the qubits that look most like transistors because I want to build a quantum computer, and we have 50 to 70 years of experience making a lot of identical devices that look like transistors. And my research, a good chunk of it focuses on making qubits simpler, because I believe that making simpler qubits leads to better qubits and ultimately quantum computers. So the research I'm going to talk about today is semiconductor quantum dot-based qubits and superconductor-based qubits and kind of combinations thereof. Why? And the reason is because building a quantum computer is a holistic problem. Anybody who's worked on quantum computing for a certain amount of time and thought about the resource requirements needed to actually perform an algorithm, a useful quantum algorithm, quickly, I think, comes to the conclusion that there's a conservation of pain. You can make the best qubit in the world at the quantum layer down below, but if it requires an insane amount of wires or complicated control, then you've just shifted the problem to another layer in the stack. And so you really need to optimize this whole system if you want to make progress. And quantum computing, building a quantum computer is hard. Why is it hard? One, you need a lot of qubits. The cost of the algorithms that we have strong faith will provide value likely require hundreds of thousands to millions of qubits. All those qubits need to be touched quite often, very differently from a classical computer, which has a extremely large mux ratio, maybe 1,000 wires to 1,000 transistors to one wire, or 10,000 to 1. Qubits need about a wire per qubit. You can, and some of them need many more than that, 20 or so. You can mux them, but that only takes you so far. They really need a lot of attention. And that places, those two things places constraints on the classical control. One, you need a lot of precision to drive these analog qubits to get the fidelity you need, but you also need low power to fit within the environmental system you developed. So in a nutshell, that's why quantum computing is hard. And in order to make progress on the whole problem, you need to sort of chip away at all these different layers. I spent most of my career thinking about spin qubits. And even after 24 years since they were proposed back in 1998, I still think they're special for a number of reasons. If you look here on the left, the PowerPoint drawing of what a spin qubit looks like, you see right away, some advantages. One, electrons in silicon are very well decoupled from charge noise. The G factor is basically 2 out of free space. Plus, silicon is one of those materials where humanity has spent a great deal of effort making it extremely clean. You can chemically purify it. You can isotopically enrich it, getting rid of the nuclear spins that are basically like little qubits that would screw up your electron qubit. And you can grow epitaxial devices, meaning fully crystalline layer by layer wafers with molecular beam epitaxy or chemical vapor deposition. And silicon germanium turn out to be very low loss. So that the more you can get away, push away the dielectrics and the noisy stuff, the better your qubits and qubit operations will be. So there's a lot of things going for spin qubits, but it's still taking quite a long time to, to realize some of their potential. And I've just shown a picture here of a result that came out in the last month or so. And this is a 6-dot device of silicon quantum dots by HRL. Here we see it's actually a 2-qubit system. There's an encoding, and we'll get to that in a minute. 3 dots per qubit, and they've done a whole sequence of a very large sequence of exchange operations, or bringing the electrons together to do interactions. So this is, really a realization of a proposal from 2 decades ago, but still a lot of promise in terms of these things look like transistors. And transistors, you can make a lot of those. So this concept of encoding is very powerful in many different areas. Error correction, compression, encoding is a way to make your life simpler in many respects. And electrons, if they have any superpower, it's this: the fermions. You know, they're actually particles, and that means that you can bring them together and they interact. And if you bring them apart, they don't. You know, the coupling between them, which is due to the Pauli exclusion principle, also called the exchange interaction, is a very strong coupling. It can allow for very fast gates, but it also has a very high on-off ratio, which is nice. And back in the 2000s, when we were all very excited about spin qubits, from a theoretical standpoint, you know, it was fairly early on discovered that you could do universal quantum computation with just the exchange interaction, which is nice because it's fast and has a very high on-off ratio, provided you go to an encoded scheme. And that means, and this is this box down here, there are many different ways you can create a qubit out of dots. You sort of have a zoo within a zoo of qubits. So you could have two qubit encoded qubit, 3, 4, and so on. Now there's a cost to this. You know, you need more dots. You don't have a single spin qubit anymore. You need more dots. You also need more pulses. So if you have a 3-spin encoding, then you need somewhere between 20 and 40 pulses to do a 2-qubit integrated gate, which adds some error overhead, of course. And then also, now that you've picked 2 states in Hilbert space of a bigger Hilbert space, you know, if you have an 8 vector that represents the 3 dots, you can have leakage out of your Hilbert space that may not be correctable by your quantum error correcting code. So you have to be careful about that. So those are some of the negatives. What are the positives? These things are called decoherence-free subspace or subsystem qubits. I label that red because it's actually quite a red herring. You know, they were originally thought about for, they do offer some immunity to global field fluctuations, but in reality, for most of the solid state qubits we think about, the noise is local. But there are some other significant benefits when you're thinking about actually, you know, making a quantum computer. One, you don't need a magnetic field. You know, you don't have to split the spin states to do operations with a microwave field, for example. That's got some benefits when you're talking about building a system, because there's no Larmor precision. You don't have to worry about, you can effectively have 0 energy qubits. You don't have to worry so much about the timing. You don't need an atomic clock to do your operations, to sync them all up. Also, because the exchange interaction is literally just moving charges back and forth, you can do everything with DC or baseband pulses. You don't need microwaves. You don't need microwave generators, you know, in theory. You know, if you're willing to take this cost of more qubits and more dots and more pulses, it simplifies some of your control. So those are promising things. And then it comes down to, you know, how do you engineer your particular encoded qubit, you know, for the best properties. Our, you know, small contribution to this, or one of them, is what we call the Aeon qubits, always on exchange only qubit. And the basic idea is, instead of doing interactions pairwise, having a 3-dot or 3 DFS qubit where all the gates are done by doing pairs of exchanges, instead make a molecule. So bring those 3 electrons together, have the interactions be always on, and think about the qubit that way. So you're starting to make, just like you take hydrogen, you can make helium. You know, here you can take a single spin, 3 spins, and make this 3-spin object, which has the properties more or less you design. People had started thinking about that, you know, way back since the early days with cluster spin qubits. What's nice about this ion regime, and in particular, it's where the 3 spins are resonant, where the energy levels of the three dots are all almost equal. In that regime, you actually get a double sweet spot to the detuning parameters that would, charge noise that would affect the decoherence of your qubit. So what does sweet spot mean? It just means, you know, the first derivative of the energy levels as a function of the detuning, and this is this right figure here, is 0. So the first order, there's no effect on charge noise, which is nice to both the detuning parameters that affect your qubit. There's some other really nice properties too. sorry guys, I have a 4-year-old coming in. One is that the qubits maintain their sweet spots.
Yeah, can I tell you something?
Sorry.
You know,
Come here. All right, sorry about that. So what's nice about these Aeon qubits is that you have sweet spots, and you can maintain these sweet spots while doing DC baseband pulses, both for single qubits and 2-qubit gates, which is really nice. So you don't give anything up there. And then also, instead of taking 20 to 40 pulses to do a 2-qubit gate, you actually only have to need 1 exchange pulse, because of they're actually kind of single spin qubits in a way. They're molecules. So those are nice properties that motivated us to do that. All right, so once you have these weird new molecular qubits, we started thinking about how to read them out. And we've designed these qubits so that they always sit at their sweet spot. They're always in, you know, the optimal point. You would prefer not to have to destroy them during readout and leave that immunity to charge noise. Traditionally, when the best way, or one of the best ways to do readout of quantum-qubit quantum computers, is to use so-called Polyspin blockade readout. And it comes from, again, from this superpower of the Pauli exclusion principle. So if you look at this box in green, you have a double dot, 2 dots on the bottom, and a sensing dot on the top. And the way to do readout is simply to do a spin to charge conversion. So if I have a singlet state separate in 2 dots, and I detune one of them so that they want to fall into 2 electrons in the second dot, leaving 0 in the first, that will only happen if the state was in a singlet. If it's in a triplet, it's forbidden by energy, by the Pauli exclusion principle. And you can use that to read out whether the 2 dots were in a singlet state or a triplet state, and thus do readout. The problem is you've destroyed your qubits now. Now you have to reinitialize to some fiducial states, but it works quite well because we can have very sensitive charge sensors. So we want another way to do readout besides that with these and other types of qubits like these. So we spent some time revisiting what's called dispersive readout, or quantum capacitance. And this is the idea, and I'll get to in the next second, of using the curvature or the dependence, the dispersion of the energy bands as a function of voltage to do readout. The other way to do it is circuit QED. The circuit QED requires a transverse interaction. It requires a large electric dipole moment, which leads to loss for these spin systems. Okay, so let me just explain what quantum capacitance is if you're not familiar. The picture in the middle here is a 2-dot system. 2 dots, or physics is basically the same as 3 dots. If you bring 2 dots together, they hybridize and form 4 states, a singlet and 3 triplets. The singlet states has this noticeable curvature as a function of the detuning. So as you move the dots up and down, the energy levels change. That signal can be detected if you send in microwaves or radio frequency waves at some tank circuit. If you attach the qubits to a resonant circuit, say a 500 megahertz to a gigahertz tank circuit, and you shoot in RF waves at a gigahertz, you'll get a phase change if the qubit was in a singlet, but you won't get one if it's in a triplet, because the triplet has no dispersion, right? So that in that way you can distinguish, in theory, the 2 states. And this has been done in the spin qubit community in other regimes where the 2 states are way different for at least a decade. The contribution we looked into was, can you enhance that? So we're in this regime where the quantum capacitance is actually quite small because we're at this sweet spot. It turns out you can enhance it by modulating the voltage on the dot at the resonant frequency. And what's nice about this effect, which has been looked at in ion traps and superconducting qubits also, is that, although never really observed, is that one, the qubit frequency can be quite different from the cavity. So that instead of circuit QED, where more or less the qubit and the cavity have to be very close in frequency, here the qubit can be 50 megahertz and the cavity could be 2 gigahertz and it will still work just as well. So this we call modulated enhancement or curvature coupling readouts. And you can do it either in the sort of static case of the static quantum capacitance or in this enhanced regime of driving the qubit at the resonant frequency. It's very nice because it's QND. The qubits are always at their sweet spots. At that sweet spot, there's no dipole moment. There's actually no coupling to a transverse coupling to a cavity. And you can have this large difference in frequency and it still works, so it has a very high on-off ratio. And I'll just mention that it's not published yet, but we've been working with Wisconsin to see this, and they've seen, experimental evidence that this effect exists and it can be quite strong. All right, so I just want to sort of wrap out the spin qubit section here by saying, once you have this type of symmetric readout, where you can distinguish single and triplet qubits. One thing I've always wanted to do is revisit, for solid state qubits, measurement-based quantum computing. Measurement-based QC has been looked at a lot in photonic computing because photons don't interact naturally. Also in Majorana topological computing and other places. But for spins, we have this exchange interaction, which is quite unique. So what would adding measurements help you? And again, our big problem with encoded operations are a lot of pulses and leakage. So if you add, it turns out if you add measurements, and this is what this paper looks at, if you add measurements to a 2-qubit gate sequence, you can really reduce the number, the time and the leakage and the number of pulses needed to do 2-qubit gates. So this kind of hybrid exchange measurement-based QC, I think, is a viable path forward to making quantum computing simpler. And I want to point out that there's a lot of connections to recent work. We've been thinking about these. Spins are kind of unique that you have single spin qubits where you can do a joint measurement of the 2 spins. So you can either think of the quantum computer as having encoded qubits, 2 or 3, or you can think about it as a single qubit per dot quantum computer where you're doing joint measurements. And so in some sense, we get symmetric joint measurements for free. So when I found this paper by Friedman, Hastings, and Zinni, I thought that was quite interesting. It's a very similar kind of idea. And then these have been extended by Hastings and Ha with these new codes that use joint measurements only to create these dynamical logical qubits. And there's obviously connections also to topological computing and to diffusion-based quantum computing. All right, so that's what I wanted to say about spin qubits. Are there any questions that I can answer at this stage about some of that stuff?
Hey, Charlie, I have a dumb one.
Sure. No dumb question.
So they have, it's really interesting. We hear a lot about, different types of qubit platforms in the news and from commercial entities. Doesn't seem like we hear as much about spin qubits, at least not at the, the scales that folks are thinking about, or not in the commercially available platforms. Do you know why that is? What some of the barriers are, or are there cool things that we're missing that because we don't have these available?
I think it's 20 years there, right? Between some of the original ideas for 2-qubit gates to realization. I still remember starting as a graduate student, 2000, 2001, and we were writing a proposal to ARO for a CNOT gate of spin qubits. I think it was by year 3 to do a CNOT gate. It took, I think, 16 years for somebody to do that. So there is a tremendous amount of material science, even for silicon, even for electrons, which we know exists, right? There's a lot of new physics that happens, which are completely glossed over in spin qubits because they're indirect band gap, et cetera, et cetera. A lot of physics and material science had to be solved before you started seeing real operations. So as opposed to superconducting qubits, which are much easier to make. And I'm actually going to talk about in the next part of this talk and tell you about ways we're going to try to accelerate spin qubits. I think the barrier to entry is higher, but hopefully we're going to help lower that. I mean, a similar story could be said for ion traps. You know, if you think about how many ion trap groups there are who can really do cutting edge stuff, you know, it's changed a little bit in the last few years, but there weren't that many because the barrier to entry was pretty high. Superconducting qubits, I think, are really kind of special in that you can really hit the ground pretty fast if you have an idea.
Thanks.
Any other questions? Okay. So I'm going to talk about superconducting qubits next. Why would I be interested in superconducting qubits? Well, it's a good question because when you think about it, it's kind of amazing that they work at all. You're making antennas. You're making it artificial atoms with a huge electric dipole moment. You wouldn't expect them to be good qubits, but over the last 20 years with just amazing design progress to make these high electric dipole antenna-based artificial atoms have coherence times approaching a millisecond. And a lot of that comes down to the transmog. The transmog, I'm showing the energy levels here of a transmog qubit, which is basically an LC, nonlinear LC circuit with a large shunting capacitance that makes energy bands that are flat, very flat, as a function of surrounding charge. So charge noise really doesn't screw up your qubit very much. And what's amazing about these things is that they're easy to make. They're big. They require a single layer of metal. You do tend to want to, buy a plastis, deposition thing to do the junction. But generally speaking, you make them and they work. I, as a program manager in this field for a long time, when I spin qubit people like make one of these for the first time, they're like, holy mackerel, it just worked the first time I made it. So that's really a democratizing thing where you can make a whole bunch of different qubit designs and they work, and then you can start exploring. So I'm interested in them. I'm interested in making them better and smaller and making them more like semiconductors. So how can we take some of the good properties of semiconductors and apply them to superconducting circuits? So one thing we did first was sort of start in silicon where we know and say, well, we know in silicon and in laser optoelectronics, everything we know about making good devices in semiconductors has been making them more crystalline or making epitaxial devices. So can you make, as a first shot, a superconductor epitaxial? Can you make this sort of 3D heterogeneous thing, which is typically a substrate, surface oxides, a huge millimeter scale or micron scale at least, electrical circuits? Can you make that thing out of a single crystal? So we looked at that. I mean, it's now 7 years ago. There turns out that you can make silicon go superconducting if you extremely heavily dope it with acceptor atoms. And combining that with ideas that come out from the donor-based silicon community, where you can use hydrogen lithography and an STM to precision implant dopants, even the very high density layer by layer. In theory, you can make, a completely encapsulated 3D superconducting structures. So that was the first idea. And if you can do that, one thing I was just giving we had a new staff member and I was explaining to them some of the history here. If you look at a transmog qubit, why would you make it like that? Like what, that makes no sense, right? You have this capacitor that's folded out. You don't normally, if you wanted to make a capacitor, you would just make a parallel plate capacitor, right? So you can make a transmog qubit that's just a parallel plate capacitor. The reason you do that is to minimize, it all come back to charge noise, right? To dielectrics and loss. The astronomy community, the superconducting qubit community discovered that if the electric field of the qubit is inside the dielectric or lossy interfaces, the qubit lifetime is not good. So you spread out your qubit, make it as big as possible so that the electric fields are in vacuum or the very good substrate like silicon or sapphire, and your life gets better. But if you could make everything epitaxially in this theory world that I like to live in, you can make a transmog qubit just like a parallel plate capacitor, right? So, dimensions then, instead of, millimeters or at least hundreds of microns, are a micron. So you can make a transmog qubit that's a micron wide. The tunnel junction is made completely, the barrier is made of silicon or maybe germanium, which is extremely low loss, completely crystalline, no defects. That's the dream, right? That's the dream.
Could you say that again?
Sorry, Siri. So that's the dream. So we presented that a while ago. And this is where, I like to talk about impact. If you work in the government, you can now try to enable other people to make these kind of advances. So before I get to that, I'll just say one step we took in this sort of transition from semiconductors to superconductors was thinking about, well, we have these concepts of encoded qubits. Can you apply them to superconducting quantum computing with benefit? So say you want to make a superconducting quantum computer that doesn't need microwave gates, doesn't need microwave generators. Well, one way you can do that is to use a 2-qubit encoding with tunable qubits. And you can design pulse sequences to do 1 and 2 qubit gates without microwaves, which is the nice thing. And so we did this paper with Will Oliver's group at MIT, where we looked at actually molecular qubits made out of 2 transmons. And they're actually quite interesting because the gap of these qubits is like 50 megahertz, not bigger than temperature, right? Right in there with, a dilution refrigerator temperature. So these are hot qubits, and you could still do 1 qubit gates at 3 nines fidelity. So it sort of busts some of the notions around temperature and what's going on in superconducting qubits. So it's really interesting first steps. And I'll just highlight here that normally you make a tunable qubit by a squid in a flux line to do tunability. But if you replace that with a nanowire, you can make a voltage tunable qubit. And a lot of gate-mon work has emerged out of Leo DiCarlo's group, Charlie Marcus's group, a lot of the investments in Majorana type physics. And so we were like that because it lets you make a voltage tunable, CMOS compatible qubits now. Okay, so getting back to the story of how to make superconducting qubits smaller. So if you could make this parallel plate transmon, now you have 1,000 times smaller qubit. And if it's really fully epitaxial, it could actually even be better, right? So that's kind of nice. And I think, it was the right time to start thinking about that because we had, people have tried to make superconducting silicon and other things for decades. But really, the last 10 years have shown, significant progress in transparent barriers between semiconductors and superconductors, largely driven by motivation to make a topological qubits, and largely in 3/5s. But there's a lot of really nice progress showing that maybe it's time to revisit the material science of making these things, and maybe it's possible. So we seeded a program called NEXT, New and Emerging Qubit Science and Technology, and we asked, what are the new materials or fabrication technologies that could realize this, and there were other types of qubits in that program as well. But here's some examples of what came out of that. You may have heard, some of them, this started 5 years ago. You may have heard some of them in the news over the last year. One of them is, well, how else could you make a parallel plate transistor, parallel low loss capacitor? Well, in theory, you could use van der Waals materials. Like you take a 2D material, superconducting 2D material, you put in hexaboron nitride, 2D materials, you cap it. There you go. You have a very small parallel plate capacitor that could act as a transmon or a very low loss capacitor. When we started this program, we didn't know if it would work. These things are exfoliated, like it's Scotch tape, right? And then we don't know if there's a good dielectric. It wasn't obvious that hexaboron nitride would be a good dielectric. It turns out it actually is. And there's been a lot of progress on making these things. The coherence time is still pretty low for various reasons, but there's been a lot of progress. And there's other ideas for making flip chip type super devices and so on. So a lot of interesting things coming out of that idea. And I'll just put in a plug for some of the work we're doing on, what can you do with something that's not quite a full tolerant quantum computer yet, like an arrays of superconducting qubits. This is a project of one of the talented people in my group, Yuri Vinet, who helped design with MIT an array of superconducting qubits and many body experiments you can do on those things, even if you don't have full control of all the qubits and interactions. So some interesting papers there. Okay, so any questions on superconducting qubits? Okay, so now I'm going to talk about, I'm going to take a step up and just talk about what we're trying to do at LPS that's new to, to help move some of these topics forward. So last year we launched the LPS Qubit Collaboratory. As you might know, the National Quantum Initiative called for NSF and DOE to stand up National QIS Research Center. So DOE had 5, NSF has 5 now. The DoD and IC put forward a few of our own. So DoD put forward 2, and this is the contribution from the intelligence community, the LPS Qubit Collaboratory. And it really has 3 missions in support of the National Quantum Initiative. 1, to pursue disruptive fundamental research, mostly in new types of qubits for quantum computing, but also looking at sensing and transduction. So this is really bulking up the lab, LPS, the lab at the University of Maryland, doubling the number of labs, hiring many more people and so on, expanding to different areas. 2 is build the quantum workforce. We're fortunate to be in a very exciting time. Where there's a lot of industry, national lab, academic interest, and people. We need people to come to the government too. We've been fortunate. I'm very fortunate to work with some really talented people, but we need to keep that pipeline going. And I think a big part of it, our thesis here, is that getting people experiences in the government when they're students will help some of them decide, this is an awesome place to work and have, impactful career. So that's number 2, why we launched this. And the 3rd is to create new types of partnerships. So traditionally, LPS has done 2 types of quantum computing or quantum research. One is very much in the DARPA model, where we work with ARO to fund programs in quantum computing across the country and internationally. The other is to do research. Like I have a research group, there's other research groups at LPS, people just doing research. And this is sort of a hybrid where instead of posing, a challenge and asking for milestones and what your idea is, what we've done is we've posted the questions. We said, here are the things we think are important and are hard. Come work with us to try to figure out how to solve them. Don't give us your ideas. Tell us that you're interested, you think you can contribute, and let's work on them together on these sort of longer term, really hard things like material science, where there really is quite a big parameter space, and it's going to take a long-term investment. And I'll mention that a big part of this workforce thing is setting up relationships with universities around the country. We helped launch the MIT Center for Quantum Engineering. We've been a long-time partner of University of Maryland, JQI, and so on. Okay, so with those 3 goals in our mission, we try to create a new way to engage. So we worked on a collaborative BAA or broad agency announcement, which actually allows government researchers and people from industry, national labs, academia, to work with us at an equal footing. So we can actually develop joint IP together. We can come up with, it's not the traditional program manager, government and performer model, but it really is a collaborative research type agreement. So we have this BAA, which is quite unique in that it allows you to basically send in a white paper saying, I'm interested, here's my skills. Let's work together for a year, either come here or just work together, virtually to come up with a research plan. If we can come up with a plan to address some of these problems, we can spend the next 3 or 4 years actually doing research. The BAA also allows, and this is important for the students and postdocs, it also creates a big national quantum computing research fellowship, which supports graduate students and postdocs fellowships. You can apply at any time. The only stipulation is that at some point in your graduate career, you get to spend a summer at LPS working with one of our scientists. So, I mean, that's a nice thing as well. Okay, so I wanted to just go through some of the initial research thrusts. So the concept here is that these will change over time, but these are the problems we wanted to put out first for people who are interested in partnering with us. The first is spins fast. So it gets right to Nathan's question, which is, why aren't there more spin qubit quantum computing groups? You know, how can we make more physics happen, exploring different types of qubits? And so there's many different ways to do it. One is to develop new techniques to make quantum dots faster or spin qubits faster. The other is to enable new professors. So for example, instead of them having to go buy a $3 million e-beam and figure out how to do multi-layer, you know, fabrication at nanometer precisions, we'll just give you the qubits. We'll make the qubits at places that already know how to make them, and we will give them the qubits so that professors can get to the measurements and then exploring different types of qubits much faster. That's another way. Just quickly through the other ones, more epitaxially better qubits. You know, again, this dream of making fully epitaxial devices, it's a hard dream. These are not trivial problems. There's a lot of different materials. The physics of interfaces is not well known. This is a great long-term problem to work on together. And at a place like LPS, our first and foremost goal is not necessarily publications, it's about moving the field forward, right? Third is, I've already talked about a little bit, these voltage controlled superconducting qubits. We have a lot of interest in that. A lot of interesting physics you can do with that systems, and I'll get to that in a minute. Going hot and not looking bad. You know, like imagine if somebody, you know, you take a superconducting qubit person or a spin qubit person, and you take away their dill fridges, and you give them a lab, but it only has fridges that are 2K, and you say, do what you can. you know, it's like my Irish, my Irish side of my family, when they came over, they didn't look back, right? You know, if you did that, what would happen? You know, would you get better qubits at higher temperature if you took away that crutch? Beyond more, before sure. Here the idea is, look, we're investing tremendous amount of resources in making ultra low loss semiconductor devices, ultra good superconducting devices. Are they good for anything else besides quantum? Can you use them for classical computing, for enabling technologies like new types of amplifiers and so on? So that's new types of use precision lithography to make ultra small transistors, things like that, atomistic fabrication. So that's the motivation there. And the sixth one is really unique. It's actually research into teaching quantum information science faster. So say I have a ASIC designer who wants to get into quantum, where can I send them for 6 months or a year and have him come back or her come back and know the lingo and be able to talk to a physicist and make progress? So we are willing and interested in funding labs, like hardware labs across the country, to create these kind of new labs for quantum where people can get a accelerated education and getting up to speed. So this BIA is open, if you're interested, please reach out, go to the website. A big part of the collaboratory as well is the Qubit Foundry. The idea here is, again, to lower the barrier to doing good physics. We started with Lincoln Laboratory. They're making superconducting qubits for groups across the country. You can literally, me as a theorist can, break out a CAD program and design a qubit and get it sent to Lincoln, and they'll make it. I don't know what I would do with it if I got it, but I can make it if I want to. So that's really cool. We're hoping to sign 2 or 3 more up over the next year. It's taking a little bit longer than normal to deal with commercial companies, but that's an exciting contribution, we think, to the National Quantum Initiative. Okay, so I'm just going to give you 2 examples of LQC projects. I wrote this sort of opinion piece a few years ago about how to democratize spin qubits. This is the same question that Nathan raised has always annoyed me. Why don't we have more spin qubits? So one proposal I put forward, in addition to, the foundry and things like that, is can we, instead of having people make quantum dot qubit chips in a traditional manner, requiring, many, many lithography steps, can you instead break up the problem, have a pristine wafer, which I can change out at any time, and a gate chip that induces quantum dots on that wafer, and allows you to do very fast characterization of new materials, to create a few number of dots, to do little, gates. If you could do something like that, and I'm not saying it's easy to do, but if you could do it, it could greatly accelerate the exploration of different types of materials, and even let you look at materials that are, very delicate. And having gone through many, many PhDs, witnessed PhDs of people just figuring out leakage, like figuring out very small details of how to fab computer chips, this would be a big enabling technology. So that's one of the things we're doing. And the basic idea here is, like, if you look at the right here, that's what you need for quantum dot. That's the simplest quantum dot you can imagine. And you can realize it in a couple different ways. So we have a collaboration, that's been going for a little while now. One way is to induce a dot with an STM tip and add the special dispersive readout circuitry I was telling you about to do readout in situ in a millikelvin STM. We have one of those at LPS. So we're doing that with silicon and germanium dopants to start. The other thing to do is to make flip chips, so again, you have your wafer, which you make at LPS and get from other places. If you make a gate chip that is sort of universally compatible, then you can now switch out your wafer, and you can look at a lot of different experiments quite much faster than you could before. So that's also ongoing. That's just one example. Another is ultratunable qubits. So if we have this dream of making a electric field tunable superconducting qubits, one way you could do it, people have done it with nanowires, with 2D 3.5 materials like indium arsenide. Another way that may be viable is with silicon germanium. There's been some initial experiments showing that you can indeed proximatize a germanium quantum well by depositing a superconductor on it. The physics is still indeterminate, I would say, how clean that interface is and so on. But that's something that's quite interesting to us, because we have a very big investment in silicon germanium for dots, both for holes and electrons. So at LPS, we've been growing quantum well, germanium quantum wells. This is Chris Richardson's group at LPS, our MBE expert, growing germanium quantum wells, adding a superconducting epitaxially deposited aluminum layer to hopefully proximatize that quantum well, and then be able to use that to make novel types of devices. And there's actually a lot of interesting physics here of these weak link systems, because now you have a semiconductor instead of aluminum oxide, and you get, pretty robust Andreev states. You basically get a quantum dot within your weak link, and the physics of that is not super well worked out, we found in the literature. So there's a lot of interesting theory here that we've been working through over the last year as we work towards making devices that are not just copies of the transmon with a weak link, but might add a quantum dots or add a lot of interesting features of solid state physics, like Cooper pair, Coulomb blockade plateaus, and so on. So there's a lot of really cool physics can emerge when you combine semiconductors and superconductors, as most of you know. So here's a new thing. I've always had this dream of making things faster and smaller, right? So one idea, again, in the superconducting realm is to, again, split up your qubits to a top or gate chip and your bottom wafer. So a big problem with making devices like this, gate mon-like devices with a heterostructure like this, is that this reverse gridded buffer layer here is actually pretty lossy. So while the silicon germanium is quite pristine and epitaxial, to get from the substrate to that part, you tend to go through a grading, step grading, which introduces defects, and that's lossy, and that can cause loss. So what people often do is they etch way down and get rid of all that, and then you have these huge overlapping things to make your weak links out of your superconductor. instead, if you could put again, these capacitors that are these wings, the antennas drive me crazy. If you could instead make vertical, like sort of a Star Wars, one of those Star Wars ships, if you could make vertical capacitors, then all the electric field is now on the interposer. So all the electric field is between these two green capacitor pads, and it's not in the substrate, right, which is lossy. So you can make this interposer as good as you want, crystalline silicon. Not only that, but now much less processing on the wafer, which is just your weak link. And again, you can replace that wafer anytime you want. It makes in theory, if any of this works, it'll make things simpler to test out different materials, and you'll get a system that may be better performing. It also integrates a DC line to do tunability. That's the orange thing that actually tunes the number of electrons in the quantum well below. That's your weak link right here. So these are the two capacitor pads. They're way smaller than in a traditional transmon, and the orange is your gate tunable weak link. So that's the 3D voltage tunable qubits. That should be in the archive soon. If you do the analysis, we find at least an order of magnitude improvement in coherence time, because all the electric field most of it is not in the substrate anymore. And then you can take the next step and make couplers and a lot of interesting things, with this system. So I'm super excited about that. And, we've looked at it for germanium, but obviously you could do other types of 2D materials or 3.5s or whatever. And part of the LQC is to explore those different routes. So this is a collaboration with Lincoln Labs and the University of Arkansas. There's Tom and Kyle and U Churchill in Arkansas. It's been a really fun collaboration. We hope to expand that over the next year. Okay, so I'm about out of time. Happy to take any questions here, or I could tell you a little bit about the NQI stuff if you want to hear about it. Sure.
Can I ask a quick question?
Yeah.
So
76.
Right.
So
So
okay. Go ahead, Peter.
I think it's on the previous slide. So we talk about this. You made an analogy with the transistors. You wanted to look at qubits that look like transistors. And I recall some years back, there was an effort to make a double gate, I think on the slide before actually. There was an effort to make double gate transistors. And the idea was indeed to eliminate the effect of the substrate, but also to create two gates, and with two gates control channel more effectively than with one gate. And so is this an equivalent of basically double gate transistor in the qubit space?
Well, I don't know what double gate transistors are, but it sounds like gate all around transistors or FinFETs, where you've now made a fin and you put your gate all around
Right.
to constrain it. This is
probably
the
an actualization of that. Yeah.
This is the opposite of that.
The opposite
And
of
the
that.
reason is that's like the worst thing you could do, right? Because when you do that, you're making dielectric interfaces all over the place. Here we're trying to push the interfaces away and anything lossy away. So we've purposely pushed the gates away from the qubit. Right, the quantumness, the nonlinear part is down here in the germanium. Right, that's the Josephson junction. These are just capacitors, right? So we've tried to push the capacitors as far away as we can, because this sort of is the exotic material, which is not perfect and introduces loss and defects and so on. And this is the thing we know how to make well with silicon vias. So it's a very similar idea, and it makes the device smaller, but kind of different in terms of why we're doing it.
Okay, and so just to get an idea of the scale, what is the scale here in roughly? Yeah,
so here's this is I don't have a scale here. So the typical scale is 100 microns to a millimeter for these coplanar things, and this is a factor of 100 smaller, maybe 10 to 100 smaller. They're still pretty big, you know, so these, for spin qubit person who thinks in 10 nanometer wire gates, these are huge. Like these green things are like 40 microns.
Yeah, okay.
They're still pretty big, yeah. And the gap is about a micron. The gap is about a micron. These guys are like 20 to 40 microns, and you can do the math. The weak link itself is pretty small. It's like a, you know, a micron or 10 microns. 1 micron or less. No,
all right, thank you.
AMI 276.
Yes, hi, Charles. Thanks a lot for the very interesting presentation. So I could you comment on the status of, like, I can see all these layer structure you talk in terms of the 3D systems on silicon and germanium, like crystals. But what is the status on this, like van der Waals epitaxial structure, for example, this two-dimensional monolayer transition made of like chalcogenides, or what are the prospects or the roadblocks right now we have on?
Yeah, so sure, I'd love to. A few groups doing this. I'll just mention, you know, the two we supported were MIT, Will Oliver's group, and BBN in Columbia. Both have now made qubits or qubit-like things. So the MIT group, there's a couple of papers that have come out, one very recently, where they've made a parallel plate, I call it a parallel plate transmon of, I think it was tungsten selenide. It's some superconducting 2D material, hexaboron nitride, and that's the critical piece, the dielectric, the insulator, and another superconducting 2D material. They've made the 2D thing. They can measure as a qubit. I think they get something like microseconds T1. There's a couple reasons that cause that short T1. One is just the design. It's a voltage device now. There's a nearby voltage gate. If you're not careful, you can, you know, you have a 50 ohm line nearby that can cause decoherence. That's one. There's also gunk. You know, there's junk on the surface that needs to be cleaned up. So those are the things I think that are limiting performance. The really important result was the measurement of the loss of hexaboron nitride, which is shown to be not quite as good as silicon germanium, but quite good, you know, good enough to make much better qubits. So I think qubits can be made out of this. Whether they can be scaled and whether it's the right material is a second question. It's like, one is just for me, this is like a proof of concept. And then obviously there's all this really cool stuff going on with the moire pattern, twisted stacks, and you can do a lot of cool physics with these systems as well.
Thank you.
We have time for one more question. Is there one more question from the audience?
So I'll just leave you with the last slide, which is, you know, visit us at quantum.gov and learn about everything that's going on in the National Quantum Initiative and my team at the National Quantum Coordination Office. So
Charlie, maybe you can just tell us, you know, for this next year, what's your biggest hope? What's in terms of a demonstration or achievement in the field? Oh, in the whole field of quantum computing? Well, it'd be nice to see quantum error correction really achieved in the next year or two. It's within grasp. I think, you know, that's probably what, that's, you know, if you look at the roadmaps from 10 or 20 years ago when everybody wrote roadmaps, you know, we're on like step 3 of like a 20-step process, right? if you want to get depressed, go back and read those. And like, I think step 4 is like the first LQB, and then the next is the LQB where P out is better than PN, right? So that for quantum computing, those are really the next two. But I think a close second are these improvements in qubits, you know, new types of qubits, as you know, stuff you're working on, topological qubits, all these other types of qubits that might help get us a factor of 10 a little bit closer, you know, in terms of fidelities. That'd be a big demo as well. Fantastic. Well, thank you, Charlie, for a wonderful talk and a great tour through several types of qubits. We are all ready to just qubit now after your presentation. Let's thank Charlie. Big round of applause. Thank you everyone for joining today. And with that, have a wonderful rest of your day.
Thank you.
Thank you, Charlie.
Yeah, thank you.